Hey guys, so welcome. Today we're going to talk about gas laws, or actually the introduction to gas laws, to kind of give you an explanation as to why gases behave the way they do, which will in turn give you a better understanding of the relationships between the different variables we're going to be talking about, such as if pressure increases in a container, what happens to the volume of the container, and vice versa. We can also start thinking about if the volume increases, what can we expect temperature to do, and vice versa. If we increase the number of moles, what happens to the volume? Okay, so just relationships like that. All right, so to start off with gas laws, you need to understand what pressure is. So, what is pressure? It is a force exerted by a gas over a given area. Okay, so what causes this force? Or what causes this pressure, rather? It's the collisions of the gas particles with each other and the walls of the container. Okay, so if you think about this little red car right here crashing into the green car, then the collision, the contact in between those two cars causes pressure. Okay, so again, the more collisions we have of these gas particles, then the more pressure we should expect to see. Okay, so let's go ahead and take a look at this scenario right here. So which shoe creates the most pressure? So is it going to be the high heels, the sneakers, or the snowshoes? Okay, so I'll give you a second to think about it. Okay, and you should have picked the red heels. And the reason being is because the smaller the area of contact, the larger the amount of pressure exerted by an object. Okay, so it's kind of, if you think about it, it's kind of like walking on your tiptoes all day versus wearing sneakers. Which one are you going to feel more pressure with? Okay, and that's going to be obviously walking on your toes. That's a lot harder than walking on your feet like you normally do. And then when you look at the snowshoes, the purpose of snowshoes is to disperse your weight over a greater area. So that way, when you're walking in 3 feet of snow, you actually don't go through the snow, and you actually walk on top of the snow. So the snowshoes would actually create the least amount of pressure. Okay, so as far as units of pressure, there are 4 units of pressure that we are going to focus on. That's going to be atmospheres, represented as ATM. We also have millimeters of mercury, kilopascals, and pounds per square inch. As far as how they relate to each other, one atmosphere is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals, which is also equal to 14.7 psi. Okay, now, as you can expect, because we have these conversions, okay, we are going to be converting between the units of pressure. So if we take a look at our first problem here, how many kilopascals are equivalent to 880 millimeters of mercury? Well, this is kind of like stoichiometry a few units back. Okay, so if we have 880 millimeters of mercury, that's our given. Okay, we would actually have to take a look at our conversion factors. Okay, so if we are given millimeters of mercury and we're asked to look for kilopascals, well, this is going to be our conversion right here. 760 millimeters of mercury is equal to 101.3 kilopascals. So just like in Stoic, in order to cancel out millimeters of mercury is going to be the one that's on the bottom of our conversion factor. And whatever we're looking for, which in this case is kilopascals, is going to be on top. And then again, your values for those conversions, 101.3 kPa equals 760 millimeters of mercury. So to solve, we're going to multiply 880 millimeters of mercury times 101.3 and then divided by 760. Okay, so you should get an answer of 120 kPa. Okay, so if you want to try the second problem on your own, go ahead and pause the video at this time. Okay, so it says calculate the number of psi that are in 2.60 atmospheres. Okay, so that means we are going from atmospheres to psi. So remember, our conversion factor is going to be 1 atmosphere equals 14.7 psi. And in order to cancel out your units, ATM must be on the bottom and PSI needs to be on top. So to solve 2.6 times 14.7, you should get an answer of 38.2 PSI. Okay, so this brings us to temperature. So for gas laws, whenever this entire unit, okay, temperature must be in Kelvin. Okay, this is absolute temperature. So if you remember, in science, we do not use degrees Fahrenheit. We always use degrees Celsius. So if you take a look, they have a difference of 273. So in order to find or to calculate for Kelvin, all you have to do is take your degrees Celsius and add 273. Okay, and of course you can always work backwards as well. So if, for example, your problem is asking for degrees Celsius, then all you would have to do is the opposite. You would subtract 273 from Kelvin to find your degrees Celsius. Okay, so practice problems. Again, that's your formula to find Kelvin. Just take your degrees Celsius and add 273 to that. Okay, so if we have 32 degrees Celsius, how much would that be in Kelvin? So 32 degrees Celsius plus 273, we should get 305. Okay, so our second example, if you want to try this one on your own, do some really quick mental math before I start explaining. Okay, so how much is 75 degrees Celsius in Kelvin? Well, 75 degrees plus 273, and we get 348 Kelvin. Okay, and then of course, like I was saying earlier, if you want to go from Kelvin to degrees Celsius, you would just do the opposite. You would subtract 273. Okay, so behavior of gases and kinetic theory. So this is where all your explanation is going to be on why gases behave the way they do. Okay, so kinetic refers to motion. Okay, this is something that you should be somewhat familiar with. You guys should have talked about this at least in middle school. Potential energy, kinetic energy, or yeah, it should be familiar. So the energy that an object has because of its motion is called kinetic energy. Okay, and kinetic theory states that the tiny particles in all forms of matter are in constant motion. Okay, again, it has to do with movement. So since gas particles are in constant motion, there's your connection there, kinetic theory and the movement. Okay, so you guys do have access to Discovery Education. I believe you have to go through Clever through this or whatever platform your school is. But just follow this link and go ahead and watch this. It's a few minutes long, but it kind of goes into detail about the molecular theory, and it has some animations in there too. Okay, so if you have time, go ahead and watch that as well. Okay, so if you can't watch the video, that's all right. I'll go ahead and give you a brief summary of what that video was. So basically, a gas is composed of particles, usually molecules or atoms, that are far apart from one another in comparison with their own dimensions. Okay, particles are relatively far apart from one another, and in between them is empty space, which makes sense because gases, we consider those individual atoms or molecules, and they're in constant motion. So that means they're just going to be flying past each other, minding their own business, not really, sticking together. Okay, so your second postulate of kinetic molecular theory is that gas molecules are in constant random motion. They travel in straight paths unless they collide with the wall of a container and then move independently from each other. So you can kind of consider gas molecules like a ball. Um, if we exclude gravity. So if you threw that ball on the floor, it would bounce in a perfectly, I guess, angle, okay, and it would just keep bouncing and bouncing and bouncing around the room, okay. So that's how gas molecules behave too. They won't keep bouncing until they hit the wall and then just keep moving from there. Okay, so our third postulate is that the molecules exert no force on each other or on the container until they collide with each other or the walls of the container. Again, going back to that little bouncy ball example. Okay, and then the average kinetic energy of the molecules of the gas is proportional to the temperature. Okay, so the explanation for this is that, remember, as temperature increases, the movement of gas particles increases as well. Okay, because kind of think of yourself. When you move a lot, do you get hotter or do you get colder? And of course, you get hotter. So gas molecules behave the same way. The hotter the temperature, the more movement they have. So that's why the kinetic energy would be proportional to temperature. Okay, temperature increases, the more movement we have, the higher our kinetic energy. Okay, and then our fifth postulate is going to be that every time a molecule collides with the wall, it exerts a force on which we call pressure, okay, which we learned earlier. Okay, so applying this knowledge, we know that gases fill their containers regardless of the shape and volume of the container. And because there is so much space between particles, gases are easily compressible. And because gases are compressible, they are used in automobile airbags and other safety devices designed to absorb the energy of that impact. Okay, and all collisions are perfectly elastic. This means that during collisions, kinetic energy is transferred without loss from one particle to another, and total energy remains constant. Okay, so again, meaning they are just going to keep moving and they are going to keep colliding and ricocheting off the walls of the container. Okay, it's just constant. Okay, everlasting. Okay, so we do have an example. So that if we consider the average speed of an oxygen molecule in air at 20 degrees Celsius is 1,700 kilometers an hour. At these high speeds, the odor molecules from a hot pizza in Washington, D.C. should reach Mexico City in about 106 minutes. Now, why doesn't this actually happen? Okay, so go ahead and take a second, pause the video, think about it for yourself. When you're ready, go ahead and push play. Okay, so the answer is that molecules are constantly striking molecules of air and rebounding in other directions. Their path of uninterrupted travel in a straight line is cut short. Okay, so those pizza molecules, they don't keep traveling a straight line. They collide with other gas particles. They bounce off the walls in the pizza shop. Okay, and then some of those gas particles we inhale into our noses. So it's pretty obvious why. Okay, the smell of pizza gets stopped short. Okay, it's those collisions with other gas particles and other objects. Okay, so what happens when a closed container is inflated? So here we have a tire. This will be your example. So think about it for a second. Okay, so your answer, pressure increases with the additional gas particles. Okay, so if we keep inflating this tire, of course, the tire is going to get harder because there is so much air in there. And eventually, if we keep going and never stop, that tire will pop. Okay, so pressure exerted by an enclosed gas is caused by the collisions of gas particles with the walls of the container. If the number of gas particles is changed by any factor, the pressure changes by that same factor until the container ruptures. Okay, so a gas inside a bicycle tire exerts a pressure of 35 pounds per square inch. So how much air must be pumped into the tire to produce a pressure of 70 psi? Okay, so if we are going from 35 psi to 70 psi, well, that's a difference of 35. So basically, we are doubling the amount of pressure we have. So if we're doubling the amount of pressure, then that means we're basically just doubling the amount of air inside of our tire. Okay, so next example, or actually, okay, so the relationship between the amount of gas and pressure is proportional, assuming that the volume and temperature stay the same. Okay, so remember, um, if we are thinking about that tire, the more gas we put in that tire, of course, the harder the tire is going to get, the more pressure. Okay, so the more gas, the higher the pressure, the less gas, the lower the pressure. Okay, so think of a tire in this case between that relationship. Okay, so if we take a look at our next example, what happens to pressure when a closed container is deflated? Okay, so if you have a closed container, and you are releasing the air in it, okay, well, do you have a lot of molecules left in that container? Okay, and your second question, okay, if you have less molecules moving around in that tire or that container, is there going to be a lot of pressure? Okay, so your answer, the pressure of the gas is decreased because there are fewer gas particles and less collisions. Okay, remember that pressure is caused by the collisions of gas particles. And if you have less gas particles, then you should expect to see less pressure. Okay, and that concludes our notes for today and the introduction to gas laws. If you guys have any questions, please feel free to comment or ask me in class.